Last page, a little bit more stoichiometry. Still using this, still using my patented 5-step process, although I think I'm going to need these sets of instructions this time. A lot more stuff with the limiting and excess. Good thing is, and if we're not honors, we don't have to calculate extra stuff, so it's not quite so difficult. First one for this one is a limiting and excess. Step 1, write the balanced equation. They don't tell it to us. We have aluminum. It's reacting with iron 3 oxide. That's Fe2O3. It's going to make aluminum oxide, Al2O3. And then the other thing is going to be iron metal. Balance that equation. I'm going to need 2 irons, and I'm going to need 2 aluminums. It's all set. Step 1, all set. Write and balance the equation. Next thing is, what do I want to know? What was I given, and what do I want to know? Limiting excess reagent has a little bit of extra notes. There's going to be 2 givens. There's going to be 2 start boxes. They both will have numbers, and they both will be reactants. So when I go start reading this, I know that both aluminum is going to be important. Put a box there. And iron 3 oxide is going to be important. Put a box there. Step 1, balanced reaction. Step 2, boxes around what I was given and what I want to know. What do I want to know? I forgot to read that part. Let me go back. It's going to ask me what mass of iron will be produced. So even though it's going to make aluminum oxide 0 moles, I don't care about that. I'm going to start with 0 moles of that. This is going to be what I want to know. This is a given. This is a given. This is what I want to know over here. Next step, everything's in grams, got to change it into moles. 35.1 grams of aluminum times 1 mole is 27 grams. That's right. 35 divided by 27 equals, I got 1.3 after rounding. 1.3 moles of aluminum, 1.3 moles. I also have iron oxide, 42.9 grams of Fe2O3. That is, let's see, iron is 55.8 times 2 is 111.6 plus another 48 is 159.6. 1 mole of that stuff is 159.6 grams. 42.9 divided by 159.6, that's 0.27 after rounding. 0.27 moles. Okay, so where are we at on our steps? We have converted to moles if it's in grams. We've set up the BCA. We filled in the start box. Now we have to figure out the want box. Next little step. Figure out how many moles can be made by each reactant. Split the box. What does that mean? When I'm over here, I need to figure out, it's kind of like the hamburgers and the patties and the buns. We have to figure out how much we have enough for. I'm going to split this box. I have enough aluminum, 1.3 moles. Let's see, 2 moles of aluminum make 2 moles of Fe. 2 moles of aluminum make 2 moles of Fe. So 1.3 moles of aluminum could only make 1.3 moles of Fe. 0.27 moles of iron oxide. 1 mole makes 2 moles of iron, or twice as much. So 0.27 times 2 over 1 would be 0.54 moles. So I've got 2 numbers over there, but only one of them is the true one. Next step, it says, circle the smaller number, cross out the bigger number. Though we have enough aluminum to make 1.3 moles of iron, we only have enough iron 3 oxide to make 0.54, so that's all we're going to get. We aren't making 1.3, we're only making 0.54. Why? Which thing did we cross out? Aluminum's number. We have more than enough aluminum, so that's going to be excess. We are limited by our amount of iron 3 oxide. This number, 0.54, came from how much iron 3 oxide we have. So we're limited by that much. So our limiting reagent is Fe2O3. We don't have to do this part. Okay, next step. Where am I at in my balanced equations? I've set up the BCA, filled in the start box. I even figured out my want box. Next step, last step, convert it to grams, because that's what we measure in when we go to the lab. How do I do that? Well, 0.54 moles of iron is what we're making. And 1 mole of iron, that goes on the bottom, so it crosses out, weighs 55.8 grams. 0.54 times 55.8 equals 30.1. 30.1 grams is the most that we can make. That's our theoretical yield. Home stretch, last one. It's a lab data. Ultimately, they're going to be asking me about percent yield. It's still stoichiometry. I'm still going to use that patented process, only I don't care about all the limiting and excess. This is actually back to being a percent yield, so I'm going to be doing a little bit of both of these. Step 1, we'll have to write and balance the equation. Do they give it to me? Nope. The person placed a piece of nickel, Ni, in silver nitrate, AgNO3, because that's a match made in heaven. It's going to make a single replacement reaction, and we're going to get silver, just a metal, so it's just an element, and aqueous nickel 2 nitrate. If we have Ag with a +2 and nitrate with a -1, it's going to take 2 of those. AgNO3 taken twice. Is that balanced? Nope. I need 2 nitrates over there. I did something wrong. Silver metal precipitated. This should have said nickel, not Ag. Nickel nitrate. Okay, back to the balancing. 2 nitrates on the right side, so I need a 2 on the left side for where I don't. Where the nitrates are. That resulted in 2 silvers, so 2 silvers. I did it. Okay. When we're doing these percent yields, we kind of have to imagine, if you really go to the lab, you have to start with some reactant. And you have to end up with product. It just has to work in that. You have to start with reactant and then with product. That helps us figure out what things are really important. When I look at all this data, it looks to me that though there's 1, 2, 3, 4 substances that we could pay attention to, the only thing that seems to be important up here is silver and nickel. So silver is over here, that's a product, and nickel is over here, that's a reactant. So the only thing that's important is silver and nickel. All the other stuff needed to be there to balance the reaction, but we don't really have to pay too much attention to it. Okay, next step. From the mass of nickel reacted. So nickel is what we are going to be given, and what we want to know about is silver. How much nickel was there? Well, they had a chunk of nickel that weighed 5.25 grams. When they were all done, it only weighed 4.89. It's not all gone. How much is gone? This minus this is going to be 0.36 grams. 0.36 grams of nickel is all that was used. Let's see where I'm at. I sort of done quite a few things. I've balanced the reaction. I've set up a BCA table and figured out what I want to know and what I was given. Although now I'm to the point where it says, box around what I was given, I got to convert it to moles if it's in grams. That's my next step. I have 0.36 grams of nickel. 1 mole of nickel, according to the periodic table, is 58.7 grams. 58.7 grams. 0.36 divided by 58.7 equals, that is 0.006. 0.006 moles of nickel. Now I'm done with this. I've converted it. I've set up my BCA. I got to fill in my start box and figure out my want box. That's where I'm at now. So my start box is 0.006 moles. When I look at the ingredients, 1 mole of this makes 2 moles of silver, twice as much silver. So 0.006 times 2 over 1 equals 0.012 moles. So I'm going to get 0.012 moles. How much does that weigh? Because I really don't have a theoretical yield yet, except I do, it's just in moles. That's going to be silver. 1 mole of Ag, which is silver, weighs 107.9 grams. Okay, here I have a problem. Moles and grams can't cross out, so I must have done that wrong. I'm going to backtrack. 1 mole of silver is, gotta go look again, 107.9 grams. 107.9 grams. 107.9 times 0.012 equals, we're only going to get one, we should only get 1.29 grams. 1.29 grams of silver. Theoretically, how do I know that's theoretical? Because when we're doing these theoretical yields, when we're doing lab data like this, when we're doing lab data, theoretical comes from fancy BCA math. That's just what I did. It's not based on lab data yet. It's just based on how much stuff we had. Now it's time to figure out how much we actually got by simply subtracting from our lab data. So let's go look and see what's going on. Well, we had a beaker that was empty. That's 102.05. And once we had our product with the silver in it, and now weighs, looks like I'm subtracting. It's a subtraction. 103.13. Let me do this. Determine the actual yield. 103.13 grams minus the weight of the beaker, which is 102.05 grams. That's going to be 1.08 grams of silver. That is the theoretical yield. Theoretical, 1.08 grams. Okay, so now it's time for the percent yield. Percent yield, check my formula again. Actual divided by theoretical times 100. So if my actual was 1.29 grams, out of the 1.08 grams I was theoretically supposed to get, times 100, 1.29 divided by 1.08 equals, times 100 equals 119% yield. Okay, I did that wrong. I put the wrong one on top. Let me go check my formula again. Did it say actual divided by theoretical? It does. Actual needs to go on top. The actual is 1.08 divided by the 1.29 grams that we theoretically should have gotten, times 100. 1.08 divided by 1.29 times 100 equals 83.7% yield. Home stretch. Sketch the pH scale. It's just this simple. The numbers go from 0 up to 14. I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Everything in the middle is neutral. Everything from over to over here is an acid. Everything from over here to up here is a base. They get stronger or increasing strength, the acids do, when we go to the left. It also gets to be increasing strength of the base, increasing strength as we go to the right. Sketch pH scale using numbers, check. Indicate acids, yep. Bases, and increasing strength. All done.